Hello everyone, my name is Jeff DuBose and I'm a graduate student in the Laboratory of Prashant Kamat at the University of Notre Dame, and today I'll be talking about photoluminescence decay, specifically using the technique of time-correlated single photon counting, or TCSPC. So with that, let's just sort of jump into things. So photoluminescence decay is essentially concerned with the timescale of fluorescence and phosphorescence. So on the right here we have a typical Jablonski diagram for a molecule. So if we have a photon of light coming in, essentially we can absorb that light, and an electron sitting in the ground state will be excited into the singlet state, and then very rapidly that electron will relax back down to the lowest vibrational state, and then it'll be sitting here. And if the electron is sitting here, it has multiple different pathways that it can take to go back down to the ground state. So for example, if the electron just comes back down non-radiatively, it can do that, but it can also return back down to the ground state radiatively and emit a photon, and that's essentially fluorescence. Additionally, though, the electron can actually form a triplet excited state, and in that case what you would have is you would actually have phosphorescence, which happens on a much longer time scale and is typically redshifted from fluorescence. But this is your basic sort of simplified molecular picture for steady state fluorescence and phosphorescence. And of course there's quite a bit of information you can glean from this. But if we actually look at the time scales of these two processes, fluorescence and phosphorescence, we can actually get, additional information that can start to really describe our material pretty well. So what kind of information can we actually get? So in the case of nanomaterials, which is what our lab looks at quite a bit, we can look at energy transfer processes, also electron and hole transfer processes. We can also get indirect information about trap states in our material. So if we have a quantum dot, we can look at, what's happening with surface traps or even intrinsic trap states. Again, if we have an electron or hole acceptor, we can also look at quenching in the material. And we can also get information about bright or optically active excited state levels. And the really great thing is, if we pair photoluminescence decay also with transient absorption spectroscopy, which is a technique that our lab uses quite a bit, we can actually develop a very complete picture of the excited state processes that are happening.
So what can we actually get from photoluminescence decay? So PL decay gives us tau, the lifetime. And you can sort of think of that as, what is the average amount of time it takes for the sample to emit light. So tau is related to 1 over the non-radiative decay rate, K and R, plus the radiative decay rate, Kr.
So the nice thing is, if we have our quantum yield data, where PL quantum yield right here is the number of photons emitted divided by the number of photons absorbed, which is equal to the radiative decay rate divided by the sum of the radiative and the non-radiative decay rate. So if we've done both our PL quantum yield measurement and also our PL lifetime measurement, with these two things combined, we can actually directly solve for the radiative decay rate and the non-radiative decay rate values, and that way we can actually describe the system very well.
So that's one set of information we can get. Additionally, we can get all sorts of information on the weighting and the lifetime components. So for example, if we have a multi-exponential decay of our sample, what we can say is, the intensity as a function of time is related to, the sum over I of each one of these prefactors, this alpha sub I, and then e to the negative t over tau sub I. Again, this is also equivalent to e to the negative kt, because again, 1 over tau is equal to k, the rate. Those are sort of inversely proportional to each other. And so what happens is, depending on how we do our fittings, we can start to say, there's different weighting components or different prefactors here. And we can do a lot of interesting analysis once we actually look at the evolution of how these alpha values and these tau values change. And I'll talk a little bit more about the analysis kind of toward the end of the talk. We can also look at an average fluorescence lifetime, a tau sub average, which is calculated down here for multi-exponential decays. But again, we'll go a little bit more into analysis in a bit. So with that, let's talk about what this data actually looks like and what we're actually seeing physically. So if we say n of t is the number of excited species in this system, we can say the change in that excited state population is related to capital gamma, or which is just k sub r, the radiative rate, plus the non-radiative rate, multiplied by that number of excited state species. So what we do is we can solve this equation. We say n of t is thus equal to n sub 0, which is the initial population, and then e to the negative t over tau, or you can think of that as e to the negative kt. So what we do is we make an assumption and we say that, the number of excited state species should actually be proportional to the intensity that our detector is actually seeing. So again, our detector response is going to look something like this. There's an initial rise, and then a decay of intensity corresponding to photons being counted in this case. And so if we make that assumption, we say, the population is related to the intensity. What we can do is we can plug in I into this equation, and we say, the I as a function of t is I naught e to the negative t over tau. and that's for the mono-exponential case. Or if it's a multi-exponential decay, we can say it's the sum of over each one of these I components of alpha sub I e to the negative t over tau sub I, or again you can think of that as e to the negative t k sub I. So again, this is what we actually see as an intensity versus time, but I think it's always important when you're looking at this decay data to realize that each one of these points essentially corresponds to a histogram. Because what we're doing in time-correlated single photon counting is we're literally counting when did those photons arrive, and we're putting them in a bin, and that bin basically being a histogram. So we can think, okay, if these are photons that arrived at 1 nanosecond, that's going to be binned down here, so early time points are over here. If this is a photon that came in at 10 nanoseconds, it's going to be binned over here. So what happens is as we collect, these bins slowly increase as we put more and more photons in there, and then over time we build up the histogram. Typically what we do is we say we stop binning or we stop collecting once the highest histogram point reaches a level like 10,000 or something like that. But again, if you're looking at these decay traces, always realize that each one of these points corresponds to an actual histogram of collected photons that came in at a certain time point. It's always important to have that sort of in the back of your mind when looking at this data. So with that, I think it's sort of important to look at a simplified scheme of how the actual TCSPC system works. Now this is going to be a little bit more specific to our system. We have a Horiba fluorocube commercial system with an IBH data station hub which does timing and a nano LED for excitation. But in general, this is going to be fairly general to most TCSPC systems that are available. So what do we have here? We have a diode laser driver. And so what this does is this sends a signal which will go both to a laser excitation source and also to these timing electronics. So you have the signal that's split and goes to the laser and then this computer. So if we follow the signal to the laser, what that's going to do is that's going to trigger the laser to send a pulse of light. Typically you can have that go through a neutral density filter if you want to attenuate it and bring down the power. But essentially what's going to happen is that light's going to hit our sample. Our sample is going to be excited up to a higher excited state, and then at some time it's going to fluoresce and give off photons of emission, and those will go through a cutoff filter. Again, we want to cut down any of the excitation light because we don't want that to scatter toward the detector. That's also why we're doing this at 90 degrees, so we don't have direct scatter into the detector. But again, so our emission is going to come out through here. We're going to cut off any extra excitation scatter. Then it's going to go to a monochromator in our case, and then toward our detector, and then it's going to get timed by the timing electronics in the system. So with that, I think it's kind of important to start with the excitation sources that we typically use, and then kind of go from there. So again, in our lab for our system, we're using these Horiba Pulse nano LED lasers. Now, typically what we normally use in our lab is the 371 nanometer excitation. And the reason why we use this is for most of our materials, this is above bandgap excitation, since we're typically looking at semiconductor materials. So this is sufficient to excite electrons well above the bandgap, and then they'll go back down to the conduction band edge, and then they can fluoresce from there. Now, if you look at the Horiba website, you can see there's actually a wide variety of different excitation sources that are available. But each one of these is discrete. So if you want to excite at exactly 455 nanometers, you would have to purchase a 455 nanometer diode head and actually exchange that on the system. And now the nice thing is it is fairly simple to switch these out. You have to be a little bit careful when doing it, but the nice thing about this system from Horiba is it's very modular in the sense that if you want to excite at a specific wavelength, all you have to do is purchase that specific color of light, so to speak, and you can easily do that. Now most of these typically have about a little bit less than 1.2 nanosecond pulse width. Again, so that's sort of how fat in time is the pulse. And typically they have about a 20 nanometer volt at half max. So again, if you're exciting at 370, you want to look at emission that's quite a bit redshifted from that. There are other excitation sources that different setups use. So some people use a femtosecond laser if you're detecting very fast fluorescence. But again, this is what we typically use for our system. So I think it's also important to sort of talk about the detectors that are used in these systems. Again, from the name time-correlated single photon counting, we do have to have the ability to count accurately a single photon or electron. But in general, this is really not very easy per se. A single photon or really a single electron doesn't give much of a voltage change. So typically what we have to do is we have to amplify that signal in some way. And the classical way to amplify these signals is a PMT, a photomultiplier tube. These are fairly inexpensive since they've been around for a while. They have very high gain, but they're not very good for fast detection. But I think it's still important to talk about the basic concept. So we have is a single photon will come in, it'll interact with our photocathode, which will convert that photon into an electron. that electron will be focused through some electrodes, and it'll be essentially accelerated toward a diode or a metal plate here. And so each time an electron hits that diode, it's going to give off 2 or 3 or 5 or so, many more electrons. So it's going to happen as one electron becomes, let's say 5 electrons, and so on and so forth. Each time all these electrons are bouncing down and hitting these metal plates, it's amplifying that signal, this number of electrons. And by the time it reaches the end, it can be thousands and thousands and thousands of electrons, which gives us a very nice high voltage that we can accurately measure. So that's sort of the basic fundamentals of a PMT. Again, in our case and in many other cases, typically what's used is something like a microchannel plate detector, which is sort of a PMT but a little bit better. It has a very fast response, it's quite sensitive. It operates very similarly to a PMT. So you can see here, this is sort of a plate right here, which has drilled or milled into it all these little channels. And if you zoom in on one of these channels here, you'll see this little schematic here. So if we have our photon, which has hit the photocathode and made an electron, that input electron will actually go through and hit the inside of the channel. And each time it strikes the inside of the channel, it's going to do the same thing it did with these diode plates, just within a tiny little channel. And so it's going to go from 1 electron to 10 to et cetera, all the way down until you have a nice big voltage you can read. So that's the MCP, the microchannel plate detector. Some systems also use avalanche photodiodes, which is sort of the semiconductor version of a PMT. These are nice because they have very low detector fault at half max, but these are typically used in a little bit more fancier, expensive setups. So that's detectors. One other detector I would like to talk about is a street camera. And street cameras are, I think, interesting because it allows you to go down to very high resolution. So you can see things typically down to like 14 picoseconds. It gives you very fast collection. It also gives you the full spectrum, so all different times and all different wavelengths. So you can see here, this is a typical spectrum here, where you can see this is the time axis here, this is wavelength. So you can see you get a nice heat map of basically the full spectrum at all different times. One of the drawbacks, though, is for now, these are quite expensive, at least compared to the TCSPC systems. And of course, if you have very, very high detection abilities, you have to have very, very fast laser excitation. So if you were to use a street camera in conjunction with a nano LED with this fat 1.2 nanosecond fault at half max, you'd be limited by your excitation source. So generally speaking, if you have a fast detector, you have to have very, very fast excitation, thus typically something like a femtosecond laser. But again, I think it's still interesting to talk about street cameras because you'll typically see this data in the literature probably more and more these days because this is becoming a little bit more common. But essentially what we have is we have incoming photons that hit a photocathode, so just like in a PMT, that photon becomes an electron, and then what happens is as that electron is moving through the system, it's going to go through these 2 electrode plates right here. And across these plates is going to be a sweeping voltage applied. And essentially what that does is any photons, and thus electrons, that came at early time points are going to be swept upward toward the phosphor screen here, and that's going to actually physically encode basically when this photon arrived by allowing it to hit the screen at the higher time point. So any photons that came at early time points are going to hit up here. If a later photon comes in, this electron, as it gets converted here, it's going to hit down here. And so what ends up happening is you end up getting both color information or wavelength information and also time information. So the cool thing about this is if you take a slice, at one wavelength at all different time points, like along here, you can basically build up the same decay trace as we would normally get from TCSPC. So you can see, let's say this is 500 nanometers, this is the single decay trace there. Or what we can do is we can slice across this. So we can say, okay, at all different wavelengths for a single time point, that's essentially the spectrum. So you can see here, this would be the spectrum, but let's say this is, 0.1 nanoseconds or something like that. So the nice thing is you can get both spectral information and decay information across the whole range in which it decays. So again, I think this is sort of something to look out for. It may become a little bit more common in the future, but that's street cameras. So sort of shifting gears and going back to our system of TCSPC, I think it's important to talk about really what is the system doing to time things. And so essentially what's happening is the laser pulse is acting as more or less a start signal. And then sometime after that start signal, a photon from the sample is going to basically be timed, and that's going to act as sort of a stop. So we have these blue traces are each one of the pulses coming from the, in this case, nano LED excitation source. That's going to come in sort of a pulse train because it has a constant repetition rate. So we have our pulse coming in, that's going to excite the sample, and then at some time point later, we're going to detect a photon. So if you look at the time difference between the start pulse, the laser pulse, and then the fluorescence photon, let's say this is something like 3.4 nanoseconds, and then later on we do this again, we detect another photon. This photon now arrived at 4.7 nanoseconds. So what we do is the system would basically bin this photon and say, okay, you came in at 3.4 nanoseconds, you're going in this bin here, because again, this is counts versus time, so early time point goes here. Okay, you came in a little bit later, so you're going to get binned here, and so on and so forth. So again, you would see a nice decay trace here, but again, always recognize that there's a histogram sort of underlying each one of these points. So this is the general way that things are being timed, but there's a very important idea that we have to basically avoid, what's called pulse pileup. So essentially what happens is if we count photons, if we have too many photons coming in, we can start to unaccurately detect them, so to speak. So I'll talk a little bit more about pulse pileup in this slide. So essentially what happens is the detector and its electronics have what's called a dead time, after which when we recognize a photon is there, it takes time for the system to basically digest, so to speak, that information, and for us to be able to count another photon afterwards. So the dead time is typically on the order of something like 100, or typically even higher, nanoseconds. That's, again, very system dependent. But in essence, this is sort of a schematic of what's going on. So if we have our laser pulse, so that is part of the timing system and also excites our sample, we're going to get an initial photon, and that's going to start the process of recording the photon. But that dead time is this whole process throughout here. So what happens is if we have more photons that are coming in, so this photon comes in and also this photon comes in, both of these guys have not been counted by the system because the system is too busy taking care of this photon during the dead time. So what ends up happening is we start counting photons that arrive first, and by definition those are photons that arrived earlier, and we start to miss the photons that come later. Again, this happens if we have too many incoming photons from the sample. And if we actually look at what that looks like in terms of a simulation. So down here in this trace, we can see the black is if we have 1% of our photons coming from our sample. And if we have more and more photons actually coming from the sample, so we have more and more of this pulse pileup, you can end up seeing this starts to skew the decay trace and makes it look like it's a lot faster all of a sudden. But again, the only reason why this is happening is because we're preferentially reading the early time point photons, and we're totally missing out on these later time point photons. So the way that we avoid this is by basically dialing back the count rate, or the percentage of photons that are coming from the sample. So typically for our system, we try to keep our count rate at or below 2%. So that means roughly 1 in every 50 excitation pulses should yield a photon from the sample. So as long as you're doing that, you can generally speaking avoid this pulse pileup problem. Now in our TCSPC software, this is denoted as alpha at the bottom right-hand part of the screen. And as long as alpha is 2%, it'll be green, but if it goes above 2%, you'll see it'll turn red. Now the interesting thing is you can actually still take data if the alpha is too high, at least for our system. So you need to be very careful. It's not going to pull up a window that says, hey, check your alpha. It's just going to allow you to take the data anyway. So again, we don't want to be doing that because we don't want to skew things toward early time points. So this pulse pileup concept is very, very important because we have to avoid this in order to get accurate information. So with that, so how do we actually avoid this? In our system, we keep the alpha value low by basically changing the slit width. So we have slits that are right before our detector, and you can modify the slit opening to either allow more or less light to the detector. Now there are other ways you could attenuate and lower this alpha value. You could add neutral density filters or an iris or something like that, but this is just what we use typically in our system. So that's pulse pileup. I think the next thing that's kind of important to know is how are these electronics actually timing, and why do we have something called the dead time? So as I had mentioned before, the electronics are synced to the laser excitation pulse, and this syncing is essentially done by the TAC, the time to amplitude converter. So what is this TAC? Essentially what it does is it linearly ramps a voltage across a capacitor once it sees that start signal, and it only stops ramping voltage after a photon from the sample has been detected. So you can see that schematically here. So this blue is the photon, the excitation photon from the sample. It's been electronically synced to the TAC. So as soon as it sees that excitation photon, it's going to start just arbitrarily increasing the voltage across a capacitor. And once we detect a photon, that ramping is going to stop, and it's going to hold that voltage constant for a while. So what ends up happening is the final voltage that you actually have after a photon has been detected is directly proportional to the time at which that photon arrived. So if the photon arrived much later, this would have ramped much, much higher before it had this pause right here. And so what ends up happening, essentially, is once we have that voltage being held for a while, the analog to digital converter, or ADC, converts that voltage signal into basically a electronic signal that's then binned into that histogram bin. So it goes into one of the different channels. That holds for a while, and then it resets back down to 0, and then we continue the process. So this whole complex process that's happening is essentially the dead time. This is the system responding to that photon. So this process is the reason why we need to avoid, or the reason why we could have pulse pileup, is because this takes a finite amount of time. So again, this is why we need to keep that alpha value 2% or lower, or you'll see in some different systems 1% or lower. Again, because the system cannot respond to a photon that comes here if this photon's already being handled. So that's a little bit about the electronics in the system. Now, I think anytime you're talking about really any technique, it's important to understand what are the limits of resolution for that particular technique. And so this leads us into the idea of an instrument response function, or the IRF. So let's talk a little bit about, the ideal world versus the real world. So in an ideal case, what we'd have is for our excitation pulse, we'd have an instantaneous excitation that also instantaneously decays. So it'd have basically a delta function that corresponds to the excitation. That would, of course, cause excitation in our sample, and then it would emit and fluoresce, and then immediately after that excitation pulse, we'd have a nice exponential decay. So this would be the ideal case. In reality, of course, our excitation pulse has its own finite width. So it has its own rise time and its own little decay. So that's going to cause the sample to be excited. And we actually end up having as a convolution of the rise and decay of the actual excitation pulse, and also the rise and decay of the response of the system. Or in other words, the response here, R, is basically equal to, or it's convoluted with, the excitation pulse and also the native response of the system. So this complicates analysis a little bit, and this is why we have to be a little bit careful when we're analyzing this data because of this convolution problem. So what are some of the things that limit resolution? One of them is jitter in the electronics in the detector. So this can be on the order of tens to hundreds of picoseconds. Essentially what this has to do with the rise and fall of electronical signals in the different electronics that are in the system. However, the biggest limiter to resolution really is that finite width of the excitation laser pulse. So as I mentioned, our nano LED diode laser has a full to half max of about 1.2 nanoseconds. So what that means is we're limited by how big this pulse is in terms of what we can actually detect. So again, the instrument response function, the IRF, sets the lower bound for detection. And the IRF, in most cases, or really in all cases, of the entire system is the sum of both the IRF contribution from the detector and the electronics, and also this major contribution from the width of that laser. So you may think, wow, this is really daunting, there's a lot of stuff going on, but luckily we can measure the IRF essentially directly, or at least something that's very similar to the IRF. And the way that we do that is we actually use a non-emissive scattering solution. Oftentimes people use like silica particles in water to essentially bounce the excitation laser into the detector. So typically what you'll do is after you get your PL decay data, so that's what's shown here, this would be like the data from your actual sample, what you'll do is you'll take your sample out of the chamber and then put in your scattering solution, and then make the detector just look at your, in our case, 371 nanometer laser scatter, and that'll be this blue trace here. And so this is essentially the IRF of the system. Oftentimes, at least in our case, the software calls it the prompt, but prompt and IRF are basically the same thing. But it is extremely important to always remember to take the prompt or the IRF whenever you do TCSPC, because you not only want to see, how is your material decaying, but also like how close is it to the response of the actual system. Because what ends up happening is if you have a very fast decay that's on the same order time-wise of your IRF, that means it's a lot more difficult to be confident about your data. So if you have something that decays with a time constant of 1 nanosecond and your IRF is 1 nanosecond, that means you can't be as confident about your data because they're very, very convoluted. Whereas if you have something that decays with a time constant of 100 nanoseconds, that's less impacted by the instrument response function of the system. So, now, one thing I've noted as I've been reading through a lot of different literature on this is, according to PicoQuant and Hariba, their white papers and technical notes, they do mention that lifetimes down to 1/10 of the instrument response function, full at half max, can be recovered via Tconvolution. Now, one thing I'll say in regard to that is there's a bit of a problem in that that assumes basically perfect deconvolution and perfect sample data, which we never really quite have that. So again, as a rule of thumb, anything that's decaying on the order of the IRF, basically anything that decays nearly as fast as the IRF, basically should be thought of as detector limited or response limited. So you should sort of talk about that data a little bit with a grain of salt, because again, you cannot be as confident about that data because it's limited by your system responding to it. And as I mentioned, things that decay in a much longer timescale than the IRF are much less affected by it. As a practical consideration for our setup, when we measure the IRF of the system, it's always important to keep the slit width the same on the emission monochromator as you did for your PL decay data. So typically what you'll do is you'll have your sample data that you'll obtain, and then you'll switch that out once you're done taking data there, and you'll put your scattering sample in, and you'll get the IRF. But make sure not to change the slit width when you do that. As before, again, we want to keep our alpha low no matter what. So sometimes what you'll see is when you add the scattering solution and you're scattering the 371 nanometer laser into the detector, sometimes you'll see that alpha value will be much higher than greater than 2%. And so to attenuate that, what we can do is use an iris to basically cut down the amount of light that's hitting the detector. But again, you should always be getting the prompt or the IRF whenever you take your data, because it's important to know to actually do this deconvolution. So, wow, that's a lot of stuff that I just talked about in terms of analysis. But luckily, in terms of this commercial system that we have, it's shipped with this DAS6 software, which can basically do this convolution of the incident response function and the actual decay, so that we can get accurate fittings. So going back to this slide, as I mentioned here, there's a mathematical convolution here, but luckily this software that we have and many other softwares like this actually basically do this heavy lifting for you. But what that means is you as the user have a few parameters that you can control. One of those is the actual fit range. So what is the data that you want to include? So that's kind of shown here with these gray bars. So you can see this is sort of, the initial part of the data, and this gray bar is how much data toward the end you want to include. Something that I've found just empirically is that, as you can see, this is showing the full rise and decay of the data. Sometimes it's good to actually move this a little bit closer so you don't tell it to look at all of this rise. I'm not sure why, but sometimes it gets a little bit confused seeing the full rise and the full decay. So sometimes what you want to do is you want to basically move this a little bit to the right so you see maybe half of the rise and then the rest of the decay when you do your fitting. Additionally, as you can see, at least in this example, again, we have counts on the y-axis. You can think of counts as basically number of photons. And the max counts here are 10,000. So you can this goes from 10,000 to 1,000 to 100 to 10 to 1. Or in other words, this is one order of magnitude, 2, 3, 4. Or in some cases, they call each one of these orders of magnitude a decade. So this is 4 decades worth of data. I think it's really important to mention the fact that the data out here, which is being binned in the later channels or later time points, this is corresponding to literally, tens of photons, compared to 10,000 photons, which is being counted over here. So the majority of your decay is happening within this first decade or first, decade and a half or 2 decades. This is representative of the majority of the sample. Way down here, if you're counting 10 photons compared to 10,000, this is essentially noise. This is contributing very, very little to the overall decay. And this brings up an interesting point in the fact that you don't necessarily have to fit the whole decay range. Because again, sometimes when you do this whole fitting across the whole decay range, it can weight some of the fitting toward these time points, toward these data points that are not necessarily representative of the whole system. Again, the majority of the decay is happening within the first decade. If you go all the way out here, it can be very difficult to get a good, nice fitting, especially for nanomaterials. Again, because you're trying to fit things that are really not corresponding to much of the data. Additionally, in this case, we're graphing on the y-axis the counts or the number of photons in terms of log scale. If you were to graph this in linear scale, this would basically be so low on the line, you would not be able to see anything down here. So again, by graphing this in log scale, it sort of exaggerates some of the data points that come out here and makes it look like they're contributing a lot more than they actually are. So again, you as the user have the ability to basically say, what do I want to include? Do I think this is anything in particular, or could this just be dark counts, or could this basically be noise? You have to basically ask yourself that. Now, of course, additionally, the parameters that you also control for fitting are what type of fitting function do you want to use? Again, we typically use mono, bi, or tri-exponential decay, Again, there could be things like stretched exponentials that people use, but typically you have control over what kind of decay you want in terms of what order of the decay. You can also additionally give it different starting values, which I didn't add here, but that's another thing you can give it. Okay, so if you've done a fitting, how do you actually know that it's a good fitting other than, okay, it looks pretty? Well, so there are parameters, goodness of fit parameters, and the main one for PL decay data is typically chi-squared. Now, ideally, a chi-squared should be on the order of about 1.2 or lower, although that can sometimes be very difficult when you're using nanomaterials, which are a little bit less well behaved. But also, generally speaking, what you want to see is randomly distributed residuals. So the residuals are shown down here in the green for this example. And essentially what it has to do is the standard deviation of your fitted trace. So basically, like if you can see here, the residuals kind of go down and then up and then down. It almost looks like its own weird kind of decay trace. What this is showing here is these residuals are not randomly distributed. Typically, if you have a better fitting, the residuals should look more or less like noise. So you can see this middle trace here has a little bit better, and then generally speaking, if you have a very, very good decay fit, it should look entirely random down here. So we have sort of two parameters. We have the chi-squared value being low, and also randomly distributed residuals, which gives us an idea for how good is the actual fitting in this case. However, I think generally speaking, it's important to make a note here, especially for nanomaterials. You can almost always throw more exponentials at it, at your decay trace, i.e. try a tri-exponential versus a bi-exponential, and it'll almost always make your fit look better. However, you must always ask yourself, what is the actual physical meaning behind adding that extra exponential term? So in some cases, it's totally valid to add, a tri-exponential as opposed to bi-exponential. If you have, for example, very dominant surface trap states or donor-acceptor pair states that are occurring. But again, you have to have some sort of explanation as opposed to, oh, I just threw more exponentials at it and now it looks a little bit better. Because again, you can always make it look better, but there has to be physical meaning. And sort of to highlight that, I'll kind of zoom in on these examples that I had. So you can see this is a mono-exponential fit to this decay trace. You can see the chi-squared, or the XSQ as it's labeled, is 5, again, kind of high. You can see the residuals are very non-randomly distributed. When they move to a bi-exponential, you can see, okay, the chi-squared went from 5.0 to 1.2. That's quite the improvement. Also, the residuals look a lot more randomly distributed, but not, perfect, of course. And then when they actually fit it with a tri-exponential, okay, the chi-squared actually did go down a little bit more, and the residuals do look pretty randomly distributed. But again, you have to ask yourself, is this physically relevant? Is there meaning to this? And in Lakowitz's Principles of Fluorescence Spectroscopy book, which is sort of the Bible of fluorescence spectroscopy, they specifically mention reducing the chi-squared value does not always lead to a better fit. So what Lakowitz says in his book is, a small amount of systematic error in the data can give the appearance that the more complex model is needed. In this laboratory, and I think he means literally his laboratory, we rely heavily on visual comparisons. If we cannot visually see a fit is improved, then we are hesitant to accept the more complex model. So he goes on to further say, in general, we consider decreases in chi-squared significant if the ratio decreases by twofold or more. Smaller changes in chi-squared are interpreted with caution, typically based on some prior understanding of the system. So again, even though I've just mentioned it's good to have a low chi-squared and it's good to have randomly distributed visuals, at some point you have to kind of take a step back and say, visually, is the fit improved? And also, is a complex model actually reasonable in this case? And additionally, he makes this mention of decreasing the ratio of chi-squared. So if you go back to this example, you can see a chi-squared reducing from 5 to 1.2. That's a pretty big difference. But when you go from 1.2 to 1.04, that's not really much of a difference. So there can be an argument for sure to be made that this could actually fit to a bi-exponential. When you're going bi-exponential to tri-exponential, unless you have a really good physical reason, there's not much of a change here. The fit basically looks exactly the same. Probably don't go for a tri-exponential in this case. So again, hopefully what this is highlighting is the fact that the analysis of this data has to be done very, very carefully. And at a certain point, you really have to ask yourself, what is the physical meaning? So with that, I just have one more slide about analysis, just to kind of harp on it. Now, there are some pitfalls with this analysis. So typically, photoluminescence decay data is fit using the least squares method. Now, this method, you really have to take a lot of care in keeping your analysis consistent. So this example is from the Lackowitz textbook of two different fitting functions used for the same decay data that have very different alpha sub I values and tau sub I values. Again, alpha sub I being the pre-exponential factor and tau being the lifetime value. So you can see this I1 has a tau of 5.5 and 8, and this I2 has a tau of 4.5 and 6.7. So if you actually compare how do these two very different exponential decay equations fit the data, that is what's graphed over here. So you can see I1 and I2 are the black trace and the red dotted trace. So if you graph it linearly, these fitting functions look almost exactly the same in the linear trace, nearly indistinguishable. If you graph it log scale, again the y-axis is now log scale, you can see a tiny little bit of deviation down here. But again, this would be corresponding to less than 10 photons compared to 10,000, so that could literally just be dark current or basically noise in the system. So what's really happening in the system? We have two different equations, and it's giving us basically the same fitting function. How do we know which one is quote-unquote correct? Well, so that's kind of a problem, and a well-known problem with using least squares method. Mathematically speaking, alpha sub I and tau sub I are correlated to each other. And what that basically means is that it's possible to come up with multiple different combinations that fit the data. So the workaround is, well, fundamentally we can't work around the fact that they're mathematically correlated. But what you can do is you can keep consistent your fitting parameters and recognize this problem sort of in the back of your mind. One thing you can do is you can make sure your initial guesses are the same. So one of the things you can do is feed the system an initial guess for the decay. As long as you're keeping that fairly consistent, and as long as you're really being careful with your fitting, you can at least be self-consistent within your fitting parameters, but again, there is technically no way if you're using least squares to get around this mathematical correlation problem. So again, always just be aware of this when doing fittings. So with that, I'll give one final general note. Much of the literature on TCSPC, or just PL decay in general, if you're looking at the Lackowitz textbook or the white paper / technical note from Hariba and PicoQuant, a lot of the examples they use are for molecules or dyes. So this is the example of coumarine and ethanol. You can see it gives this very nice mono-exponential decay. But typically, it's more so molecules that exhibit a nice mono-exponential decay. And this is because they're typically more well-behaved, assuming they're nice and rigid and fluorescent. Of course, molecules can deviate from their mono-exponential decay behavior. You can have intramolecular charge transfer, or you can have excimer formation, when two excited state molecules make a dimer, or you can have different solvent effects. But generally speaking, don't be discouraged if your decay traces don't look like perfect mono-exponentials, because again, this comes from the more molecular photochemistry kind of crowd. Nanomaterials, on the other hand, which is what we typically focus on, which is why I'm harping on this, they rarely exhibit this well-behaved mono-exponential decay. So typically you'll see something that looks like this. Again, if you're graphing on the y-axis in the log scale, you'll see something that looks like this. This tells you it's multi-exponential in some way, or it could be a stretched exponential. Again, if you have a nice linear trace, this is why typically people graph the y-axis in terms of log scales, because if you get a nice line, it means it's a mono-exponential decay, or close to it. So again, why are quantum dots or nanomaterials typically deviating from this? When you compare a quantum dot to a dye molecule, quantum dots have literally thousands of atoms, depending on the size, of course, compared to something like a molecule, which is only a small handful, again, depending on the size. But it's all these different atoms that see a fairly different environment that can lead to different de-excitation pathways, specifically in the quantum dot. And one of the major ones is surface states. So if you have an atom at the surface of a quantum dot, if it's not well passivated, it'll have a dangling bond, and that can add all sorts of non-emissive pathways. Additionally, generally speaking, quantum dots have a higher interplay of both bright and dark states, so all of these things together lead you to not as well-behaved decays in your PL decay data. So just sort of have that in the back of your mind a little bit. Okay, so with that, I think I'll end this lecture or webinar thing with a few examples from the literature that I think demonstrate really well what we can do with PL decay data that should sort of highlight a lot of the things that we just talked about. So this first example that I'll give is from the Olivisados group, this paper here, where they essentially do a post-synthetic thiocyanate surface treatment to the cesium-lead bromide quantum dots. And so in this case, we're going to have an example of PL decay monitored at one wavelength. So what the authors do in this paper is they take these untreated cesium-lead bromide quantum dots and compare it to the thiocyanate-treated cesium-lead bromide. So they can see is in the untreated sample, you have low quantum yield. And additionally, from the PL decay data, you can see there's a multi-exponential PL decay. So this red is the lifetime here, and then the black trace is the mono-exponential fitting. Obviously, from this deviation, you can see this is not fitting very well, but also they give nicely the chi-squared value here of 9.2. Again, very far from that about 1.2 value that we desire. They also give the residuals down here, so you can see the residuals are very non-randomly distributed. They're kind of all over the place and have relatively high magnitude. So you can see in the untreated sample, not behaving very well at all. However, when they treat the sample with thiocyanate, suddenly you can see the lifetime is almost perfectly mono-exponential, and you can see this is the black trace is the fitting equation for the mono-exponential decay. And the chi-squared goes from 9.2 down to 1.2. So now it's behaving very, very well as a mono-exponential decay function, and you can see the residuals are much more randomly distributed. Again, they're not perfect, because nothing really is whenever you measure things, but it's much, much more improved. So sort of the interpretation here is this thiocyanate treatment is removing any surface traps on the surface, which were leading to this multi-exponential decay, leading to a single decay channel, and that's that radiative decay channel. So no, I know I just sort of spent the previous slide saying you don't typically see this. This is a bit of an anomaly. Most nanocrystals are not so well behaved, but I think this is a very interesting example of, looking at PL decay, a very careful analysis in the fittings that really represents, what you can do and some of the interesting interpretation of the nanocrystals in this case. So I really quite like this example. Going forward, so this is an example of some authors that were looking at copper indium sulfide, zinc sulfide. In this case, what they're looking at is not necessarily PL decay at one wavelength, but actually a time-resolved spectrum. So basically looking at the full emission spectrum at different times, and in this case indicating different emissive states. So you can see this blue trace here is the fluorescence spectrum, specifically for photons collected at 50 nanoseconds. So you can see it has sort of looks like two emissive states, something more in the blue and something more in the red. And then if you take the actual fluorescence spectrum at later time points, so at 370 nanoseconds, you can see this state over here is contributing more and this state over here is contributing less. So there's an evolution of actually what the spectrum looks like over time. Then even out to 1 microsecond, again, you can see two different states, and they use the Gaussian fitting to showcase state here and a state here. So I think this is really interesting because based on this this long lifetime, this redshifted emission component, they end up with, of course, other information, concluding that there's a donor-acceptor pair state in this system. And one reason why I like this is we can actually use our TCSPC system, again, to build up these traces. If we only, for example, if we do basically a PL decay trace at all these different wavelengths, and then tell the system, only show me the photons that were binned at 50 nanoseconds, what that can do is that can give you these individual traces. So if you do the full PL decay spectrum at all these different wavelengths down here, you can start to build this up, even with something like our system, our TCSPC system, and not necessarily with something as fancy as a street camera. So I think this is a very interesting example of using the time-resolved spectra. So going forward, I also wanted to show a little bit of data from an actual street camera, because again, I think this is going to be a little bit more common in the literature as the years go on. So again, this is, since it's from a street camera, it's the PL decay in spectra at all wavelengths. So in this case, the authors were looking at cad selenide zinc sulfide quantum dots with different crystal structures, so zinc blende and wurtzite cadmium selenide, and they wanted to see what optical differences there were. And so again, they're using the street camera to look at the PL decay. And so you can see again here on the y-axis is the time in nanoseconds, on the x-axis is wavelength, or in this case energy. So you can see there's a primary radiative decay channel right here, which is giving the majority of the emission. But at very, very early time points, there's a state over here that's shifted more into the blue that has a very, very short lifetime. So this is over here, a zoom in of that. So you can see again, primary decay channel here, and then this very, very, very short-lived but emissive decay channel, which is decaying very, very quickly. So using this analysis, they found a tau, or a lifetime of that more blue-shifted state of 54 picoseconds. And of course, using a lot of other information, they were able to propose an excited state model, where they're basically showing there's an emissive initial excitonic state, and then even higher order state that's a bright state up here, which is why it's so short-lived. But I think this is quite interesting because in our TCSPC system, which only has resolution down to about 1 nanosecond, which should be kind of right here, you would totally miss all the information here. So there's not necessarily a one-size-fits-all. You definitely need to have different modalities to look at different, faster processes. So with that, so this example is from actually our group, so looking at zinc sulfide, copper-indium sulfide nanostructures. And what's really going to be highlighted in this case is looking at basically the evolution of PL decay fitting parameters. So the alpha sub I or the tau sub I, the pre-exponential factors, and also the lifetimes. So in this case, these nanocrystals were synthesized with a varying zinc to copper ratio. So you can see here in the steady state PL, the PL trace actually can shift quite a bit if you change the ratio of zinc to copper. You can see for this 1-to-1 stoichiometry, you have a red emissive state and a more blue shifted emissive state. So two very different states here that are emitting. And so you can also see that there's presence of both a fast and a slow component in the lifetime. So again, here, if you take the lifetime from that more red shifted emission, you can see at 700 nanometers, it's a very slow, nice decay. And then from this state over here, we have a much, much faster decay. So what the author, Gary Zaitas, was able to do is basically carefully analyze each one of these traces, again using a multi-exponential decay fitting, in this case a bi-exponential, and then show the evolution or the change in these individual components versus stoichiometry. So what you can see here is as we actually change the stoichiometry, both the tau1, so the fast component, is increasing in time, or in magnitude I should say, and also the tau2, the slower component, is also increasing as we change stoichiometry. Additionally, here you can see this is alpha 1 divided by the sum of the two alphas. This is basically what is the contribution or the weighting from alpha 1. This is decreasing as we change the composition, and also with a concomitant increase in that alpha 2, that slower component. So the nice thing about this is using all this information, they're able to show essentially there's two different states. One is a short-lived, more blue-shifted emission with a tau of about 10 nanoseconds, and then this one is a lot more red-shifted, and it has a much longer lifetime. We can start to preferentially show more and more of this emissive state if we actually change the composition. And I think this also highlights an interesting point is, as I mentioned in a few slides back here, which I'll go back to, so as Lakowitz pointed out in his textbook, there are multiple different alpha 1s and tau, or alpha sub i's and tau sub i's, that can actually describe the decays in these cases. But the nice thing is, as long as you're consistent, or at least self-consistent in your analysis, it may not matter so much, because importantly in this example, we're not so concerned with the actual tau sub 1 and tau sub 2 values. We're looking at the evolution of those values as we change a parameter, in this case, the stoichiometry. So even if the quote-unquote real tau values are a little bit shifted lower, a little bit shifted higher, it's not so important, because if you do this analysis versus stoichiometry or versus temperature or versus some other parameter, it becomes a little bit less important the individual values and more important what is the trend as it changes. So I'll give one final example, which again is very relevant to our lab and a little bit of a shameless self-promotion. This is a paper that I recently published, basically investigating cesium bromide nanocrystals and also methylhalogen as an electron acceptor. And again, this is going to be an example of looking at the PL decay fitting parameters, the alphas and the taus. So in this case, what we had was we had cesium bromide nanocrystals interacting with methylhalogen, which is an electron acceptor. In the steady state PL, we saw a nice quenching of the PL as we added more and more of the electron acceptor. And we can also see a much faster PL decay as we increase the concentration of that electron acceptor. So the black trace here is the cesium bromide nanocrystals by themselves, and as you can see, the PL decay is getting much, much faster as we add more and more of that quencher. And I think it's kind of important at this point to show, we also show the prompt or the instrument response function as these gray squares here. And as you can see, for the highest concentration of methylhalogen that we added, the decay is very, very, very close to that prompt. So you can see, at these higher count rates or higher total counts, they're very almost indistinguishable, very close to each other. So again, we would want to be careful in specifically talking about the individual values for the components of this. It'd be better to talk about this trace specifically as more or less prompt limited or instrument response limited. But again, I think this is sort of a nice example of, to what degree do you want to actually be confident in saying this? You should probably take the actual values for this decay trace a little bit with a grain of salt. But we did something very similar as the previous paper. We looked at how does the alpha sub 1 and also alpha 2 actually change, and also what is the magnitude of the two different tau values. So you can see as we add more and more methylhalogen, we see the contribution from alpha sub 1 or A sub 1 increasing with a concomitant decrease in the alpha 2. So again, this fast component, or the tau 1 component, is becoming faster and is contributing more. And then the A2 component, or the alpha 2 component, is contributing a lot less. You can also see there's a decrease in the average lifetime as well. So that's really happening is, or what's really being told here is that the fast process corresponding to electron transfer, dominated by alpha 1 and tau 1, this is becoming the most highly dominant as we add more and more methyl biogen. So as we have more and more electron acceptor, we're basically skewing the system more toward this electron transfer component. And again, these values might change a little bit depending on your initial conditions, but as long as you're self-consistent, you should be able to see, again, the general trend is what we're more interested in, not what are the exact values in each one of these cases, because technically those can vary a small degree. So with that, I'll kind of conclude this introduction with a few little kind of final points. So similar to steady state PL decay, specifically by means of TCSPC, is extremely versatile, especially for nanomaterials, because that's what our lab uses, but it's also versatile in a lot of other fields like biology and physics and so many more, material science, etc., etc. But a lot like steady state PL decay data is actually very easy to obtain, at least for our system for TCSPC. It's sort of, once you have everything in the cuvette, you kind of turn it on, and you can obtain data very, very quickly, which is amazing. But you have to be very careful, because you can obtain traces, but the difficulty is knowing whether you actually obtained the data in the correct way, and also if it was analyzed properly, and what are the conclusions you can draw from it. So I spent a lot of time talking about the analysis, because again, this is what sort of makes or breaks PL decay. Is these days these systems are very easy to utilize. Again, it's very easy to get data, but there's a lot of pitfalls in the analysis that can sort of skew things and make it seem like something is happening, but it may not actually be happening. And additionally, in conjunction with transient absorption spectroscopy, which our lab utilizes quite a bit, PL decay data gives very complementary information and can paint a very complete picture of the excited state processes happening in these systems. So again, these two techniques together are very, very powerful. And you can see a lot of our papers try to utilize both of them to give a more complete picture. So with that, I'll point anyone who's listening still to some useful resources. The main one is Principles of Fluorescence Spectroscopy by Lakowitz. Again, that's kind of shown here. Again, as I said, this is sort of the Bible of fluorescence, steady state, fluorescence quenching, all sorts of different fluorescence techniques for biology and physical chemistry, etc., etc. It has basically everything. So I'd highly recommend this text. But if you're looking for more specific things to time-correlated single photon counting, both Hariba and PicoQuant have these technical notes or these white paper kind of things that they've made, which are extremely important and useful if you're going through and trying to learn more about this. And of course, all the publications that I talked about and highlighted in this case, each one of them is very, very interesting and gives a very, very nice example of basically PL decay and what it can actually tell us about lots of different systems. But again, this is just a very small subset, and again, very specific to nanomaterials, since that's what our lab deals with primarily. Again, you'll see this stuff being used all over the place. So thank you for listening. Hopefully this was informative, and thanks again.